Hello everyone, welcome to your lesson for today. So we are starting chapter 5 today. More work with matrices, but don't worry, today we're not going to be dealing with any gigantic matrix problems like some of the ones we dealt with early last week. We're going to start small with smaller matrix problems. And really this chapter is telling us more about the matrix. Okay, so we're going to start with smaller ones. We're going to go from there. Today, we are doing section 5.1, all about matrix operations and solving matrix equations. Okay, so the first part of this video is going to be all about matrix operations. What can I do to a matrix? Like that's what we think about when we deal with operations. Before we do that, we just need to name a few things. We need to define a couple things, make sure we're all on the same page with that. And then we'll go ahead and talk about the operations. So there are two different ways that we can represent a matrix. Sometimes you'll just see a capital letter like matrix A, matrix B, matrix C. So a capital letter represents an entire matrix. A lowercase letter enclosed in brackets can also represent a matrix. So you would either see maybe just a capital A, or you would see this bracket with a lowercase letter, but with these little IJ things, okay? A general element, we talked about elements a little bit last week, but basically a number inside of a matrix is an element. Here, we're going to denote an element by saying AIJ. I refers to the row that it's in, and J refers to the column that that number or particular element is in. So for example, if you saw A32, that would be referring to the element of matrix A located in the third row and second column. All right, a matrix of order Mn has M rows and N columns. We're also kind of introducing this term order. So anytime that you have a matrix that has a certain number of rows, it has a certain number of columns. And we talked about this like something with this X symbol something. We kind of talked about this a little bit last week, but this is called an order basically. If M equals N, if the number of rows equals the number of columns, then it's a square matrix. Right, so I could have a matrix that has A, B, C, D. It has 2 rows, 2 columns. That's a square matrix, for example. Okay, that's defining a lot of stuff. Let's actually look at an example where we can put some of this to work and make some of this make a little more sense. So we're going to start with example 1. I wasn't supposed to have the solution on this one. We're going to go to this one. What is the order of the matrix here? So again, order is really just M times N. How many rows do I have and how many columns do I have? Well, I have 3 rows, 3 columns. So this is of order 3 by 3. It's a 3 by 3 matrix. Okay, so it is of the order 3 by 3. Then they're going to say, okay, if A is represented with all these different elements of I rows and J columns, identify A23 and A32. So A23 would be second row, third column. Let's trace it out. Second row would be 1, 2. Third column would be 1, 2, 3. Second row, third column, boom, -3. So A23 is -3. A32, now we're looking at the 1, 2, third row, and then 1, 2, second column. That would be this number right here, or -2. So that's kind of the difference between the capital A's and the lowercase a's. The I is your rows, the J is your columns. And I know this is a little weird, right? Because we just said, okay, M is rows and N is columns. When you're dealing with an order, typically we'll see M by N, M for rows, N for column. I and J are also just placeholders like that. We just tend to use I and J when you're referring to a specific element, such as, A23, something like that. All right, we're going to keep going with this. We have a couple of properties that we need to talk about. We need to talk about equality. So if I have two matrices, A and B, they are equal only if they have basically the same exact numbers in every location. So down here you can see, well, if A equaled this and B equaled this, the only way that they would be equal is if X was the same as 1. That's what they're saying here. If Y plus 1 was the same as 5. That's what they're saying here. And if Z was the same as 3. So here. So they're only equal if in every location the elements are the same. All right, when I'm dealing with matrices of the same order, also obviously feel free to pause this video where you need to as you're taking notes, because there is a lot of content in the beginning. Again, you don't have to record every single word on a slide for notes. Just write what you can to make sure that you know what you're looking at when you refer back to them later. All right, here's a table below shows the matrices of the same order can be added or subtracted just by adding or subtracting corresponding elements. So over here, they're adding matrix A and matrix B. We have to make sure they're of the same order. If they're not of the same order, I cannot add them. So over here, I'm adding the element in row 1, column 1 with row 1, column 1 to get that. I'm adding the element in row 1, column 2 with the other row 1, column 2. That's going to give us 4. I'm adding these two down here. That's going to give us 3. And I'm adding these two. That's going to give us 9. All right. So when they say add or subtract matrices, first make sure they're of the same order. That's important. And then you're just adding elements in the same position. Same exact thing goes with subtraction, right? So now I see, okay, I'm subtracting. So I would do 1 minus -1 to get me 2, and so on and so forth. All right. The sum or difference of two matrices of different orders, so this is crucial, is undefined. I cannot add or subtract two matrices if they have different numbers of rows and columns, okay? So as long as they're both, a 2 by 3 and a 2 by 3, great, add them. But if they're a 2 by 3 and 3 by 2, nope, cannot do that. So let's try this out. Perform the indicated matrix operation. Well, they're saying to add, so I'm going to do 0 plus -3, -3. 4 plus 4, that's 8. 5 plus 6, that's 11. -1 plus 8, that's going to give us 7. 7 plus -4, that's going to give us 3. -6 plus 5, that's going to give us -1. And we have successfully added these two matrices. All right, that's really all there is to it. Just add them up and you are good to go. Last week, we converted systems of equations into matrices. So you could even think about, hey, maybe I'm dealing with two systems of equations right here. Look at this operation that I'm performing. This would be crazy to perform this with the actual equations. Like, that would be a lot of work, but converting them into a matrix and then performing the operation, well, that actually kind of simplifies it for us. So I think in this chapter, we might start to see that, hey, sometimes doing the whole matrix process for certain problems, not for all of them, but for certain problems does actually make it a little easier. Okay, let's keep going. Here's another one. Perform the indicated operation. So try to pause the video, do this on your own, and then skip forward and check your answer. And I will be working it out up here. All right, so I'm going to do -7 minus -6, or plus 6. That's going to give me -1. To do 8 minus 7, that's going to give me +1. 3 minus 0, that's going to give me 3. -4 minus -5, or plus 5, that's going to also give me 1. And that would be our solution here. I just took each element in the same location and subtracted them. All right, we're going to define another thing here. A matrix whose elements are all equal to 0 is called a zero matrix. So if I had like a 2 by 2 matrix, but all of the elements were 0, that would be an example of a zero matrix. So if A is an m by n, I could have any number of rows and columns, and 0 is the m by n zero matrix, again, any number of rows and columns, but if the number of rows and columns matches here, then that first matrix A plus your zero matrix is still just going to be A. This is called your additive identity. So the m by n is called your additive identity here. For any matrix, the additive inverse is written as just negative A, what that means is that if I added these two, it would end up giving me a 0 matrix. So let's do a little more work with this. Basically, the negative of my matrix would just be find the opposite of every single element in your original matrix. That would be it. So for example, if I had 2, -3, 4, 7 as matrix A, well, the negative of that would be -2, +3, -4, -7. If I were to add those two matrices together, it would give me 0, 0, 0, 0. All right, so negative A is the additive inverse, and your 0 n by n matrix is your additive identity. All right. Here are a few more properties on the next slide. Again, pause this video as you need to write down what you need to. Take your time with this today. Again, it is a lot of content, and then we'll get into more problems in the coming days. So properties of matrix addition. If A, B, and C are m by n matrices and 0 is the m by n 0 matrix, then the following properties are true. I could add these in either order. That's your commutative property. I can group A and B, or I can group B and C when I'm adding all three of them. That's your associative property, right? You've dealt with these in other classes. Now we're just applying those same properties to matrices. Your additive identity is just saying, hey, I can add 0 matrix to A. It's still just going to be A. And then your additive inverse is saying, hey, if you take your inverse matrix and add it to your original one, it's always going to result in 0. Another thing that I can do to any matrix is I can multiply by what we call a scalar. So a matrix of order 1 by 1, such as this one right here, that is a matrix, believe it or not, 1 row, 1 column. It's just one number. That is a matrix. It just contains one entry. To distinguish this matrix from just the number 6, we would refer to 6, just that loose 6. It's not a matrix. It's not in a matrix. It's just 6. We would call that a scalar. Okay, I can multiply any matrix A by scalar C. So this is really just representing a number, such as the 5 that you see down here. I'm taking this scalar 5 and I'm multiplying it everywhere in my matrix, and I end up with -35, 40, 15, -20. Okay, so scalar multiplication is just, hey, here's a number, multiply each element by that number. That's all that it is. Again, pause if you're writing notes. Here's the example we're going to do. So they're giving us matrix A, they're giving us matrix B, they're asking us to find -4B. So -4 is our scalar, and I just want to multiply this with every single element in my matrix, which would give me, well, -4 times 3 is -12, -4 times -4 is +16, -4 times 5 is -20, -4 times -7 would be +28. This right here represents -4b. That is scalar multiplication. I multiplied each element by -4. Now we can start to expand this a little bit. We can even get into equations almost. We're not going to do that quite yet, but you could start doing things like this. Do 2 pieces of scalar multiplication and then add those resulting matrices. Okay, again, if a matrix is representing a system of equations, this would be a very complex process for us to do with equations. But if I boil it down to a matrix, well, now it doesn't seem as bad. So I'm going to do 2 times matrix A, -2, 5, 4, 0, plus 3 times matrix B. Let's start with this one. Multiply each element by +2. That's going to give us -4, 10, 8, and 0. And then I'm going to want to add that to this one. Over here, I'm doing scalar multiplication by 3, which is going to give me 9, -12, 15, and -21. Okay, final piece is just doing matrix addition. So I need to add these two, and that is going to result in -4 plus 9 is 5. 10 plus -12 is -2. 8 plus 15 is 23. And lastly, 0 plus -21 is -21. And this is our solution to 2a plus 3b. All right? We can do a lot of stuff with multiplication. Matrix multiplication gets a little more complicated. That we will talk about later. For right now, we're going to stick with just scalar, so multiplying a matrix by a number. These properties are true. If you want to multiply two scalars by a matrix, you could either multiply the two scalars first, or you could multiply one of them by the matrix and then multiply that new matrix by your other scalar. 1 times A is just A. That's kind of your multiplicative property. And then if you have something like this, you can kind of think about distributing that scalar. You can multiply A by C and then add it to C times B. Or you could just add those two matrices first and multiply the result by C. You have some options there. I'll clear that so you guys can actually see what's being written. And then similarly, you could do that same kind of process. You could add your scalars first and then multiply, or you could kind of distribute your matrix. Do it either way. Okay, so these are just a few properties of scalar multiplication. We are going to end on example 4. This is your last example. Solve for x in the matrix equation 2x plus ab, and they're giving us a and b. Easiest way to tackle a problem like this is to rearrange by solving the equation for x. So solve equation for matrix x. I'm going to do that by subtracting a. That would give me 2x equals b minus a. And I'm going to divide everything. Sorry, I should make this a capital X. It is still representing a matrix. Divide everything by 2. So we ended up getting matrix X equals 1/2 times b minus a. Because we haven't really talked tons about division, I rewrote this as 1/2 times b minus a. That's going to be a little simpler for us right now. Okay, so I know anytime I'm dividing something by 2, it's the same as multiplying by 1/2. All right, let's start by combining up those two matrices. Start with this part right here. So I want to do b, -6, 5, 9, 1, minus a, 1, -5, 0, 2. So b minus a is this. What's -6 minus 1? -7. What is 5 minus -5? That's going to give us positive 10. What is 9 minus 0? That's going to give us 9. And what is 1 minus 2? That's going to give us -1. So this matrix represents b minus a. Then the last thing we have to do here to solve for x is multiply this entire matrix by 1/2. And yes, it is possible. Now we're going to start introducing more fractions into our matrices. So this is going to leave me with -7/2. 10/2, or 10 times 1/2 is the same as positive 5. Then I'm going to have 1/2 times 9, which is 9/2, and -1/2. And this is our solution. We have successfully solved for matrix X. That's your solution right there. All right, folks, good work with this. Carry on, get started on your homework. If you can complete it in class, that's awesome. And I will see you all tomorrow.